So up to this point, I've given you kind of a high-level overview of what Java synchronizers do. I said there's mutual exclusion, I said there's coordination, and then there's some variations on those things we'll talk about. What I want to do now is kind of just give you an overview of the pervasiveness and complexity of Java synchronizers. And I'm going to kind of show you where they reside in the stack of software that you will find on modern Java platforms, which would include the Java platform, TM, right, Java, or Java-esque platforms like Android, which aren't quite Java TM, but they're got pieces of Java in them, for better or worse. And as we'll see, there's Java synchronizers that occur in the execution environment level. This is like the Java virtual machine or the Android runtime, and those include volatile variables and built-in monitor objects. And then there are also different kinds of synchronizers that occur at higher layers like Java atomics, locks, and other synchronizers. And we'll also talk about the complexity of synchronizers, because synchronizers are often used to deal with very complex coordinations and interactions. Anybody know where this is, by the way? Exactly. I was in India about 10 years ago, and I was in Bangalore and Hyderabad, and I had lots of experiences with traffic very much like this. In fact, one of the things that I found most fascinating was that I was usually in a taxi cab, and that Indian taxi cab drivers seem to have ESP, because they can get their cars right next to the person next to them, and somehow magically they don't run into each other. I do not understand how this works, but it looks like this a lot. It may be different now, but it was quite funny at the time. Okay, so there are multiple layers of synchronizers provided on the Java platform, and some of the features are in the Java execution environment itself. That is, they're baked into Java. So if you think about Java, Java has a couple different layers. It's got the Java execution environment, and things like volatile variables and built-in monitor objects reside there. Those are typically implemented in C or C++ with a thin Java JNI-like wrapper around them to give them a Java facade, but they're really implemented in lower-level languages. There's also a whole slew of things that are implemented at the higher layers. These are what we would call the Java class library. And again, without getting into too much gory detail, the Java platform has a bunch of different layers. And the stuff that exists at this layer is typically largely written in Java with a few callouts to lower-level helper methods or helper classes written with JNI, the Java Native Interface, which wrap around C and C++ native code. We'll talk a lot about that because we're going to look at some of the implementations. So let's talk about some of the complexities. So why is synchronization complicated? Well, it's complicated because there's interactions between two or more entities that are running concurrently. And the minute you have a bunch of things that execute concurrently, as you know from everyday life, be it traffic jams or trying to organize a team project for your software engineering course or whatever, once you've got more than one thing happening, you've got to coordinate stuff. You've got to synchronize stuff. You've got to deal with the complexity that comes from interactions. There are two general types of synchronization complexities. And this discussion is loosely based on a paper written by a famous software engineer named Fred Brooks called No Silver Bullet. And he identifies two kinds of complexities: inherent complexities, or what he calls essential complexities, and accidental complexities. So inherent complexities are things that are simply inherent or fundamental challenges in a given domain. Here we are in the domain of synchronization. And there are certain things that kind of constitute the rocket science. So one of them is mutual exclusion, as we talked about before, which is necessary to ensure concurrent threads don't simultaneously run within a program's critical section or sections. And the typical phrase you will hear used for this is called race conditions. And a race condition arises when the proper functioning of an application depends on the sequence or timing of how the threads are scheduled and run. And if you're lucky, they will run in a certain order at a certain time and everything will go well. If you're unlucky, which is usually most of the time, by the way, especially if you're doing a production run for an important customer, or you're trying to control the nuclear reactor temperature gauge, or you're trying to make sure the airplane maintains its proper altitude and flight program and so on, things will go awry and you'll get corruption. Another inherent complexity is coordination, which, as we talked about before, it's managing the order or the time in which operations are performed to ensure threads access either application or system resources correctly and efficiently. And you can think about, a good example of this if you ever fly airplanes, if anybody ever travels anymore. Probably travel much less than you used to by airplanes. But when you do travel by airplanes, someone has to coordinate all those airplanes so they don't run into each other on the runway or in the air. And that's an example of coordination, which, by the way, is having a hard time these days for a variety of reasons in our air traffic management system. And yet a third type of complexity is deadlock, which occurs when two or more competing actions wait for the other to finish and none ever do. So you end up in this kind of like a standoff situation where different threads own different resources and they're stubborn and won't give them up to anybody else. So those are inherent complexities. There's also a bunch of accidental complexities. And these complexities arise from limitations with the techniques, the tools, and the methods that we use to synchronize programs. By the way, there's accidental complexities for lots of other stuff too, but I'm focusing solely on synchronization here. And you can read about accidental complexity here. I think it might even mention me somewhere there. These are problems that arise because tools are often not sufficient to debug concurrent programs effectively and correctly. Think about how we used to debug problems with health. If you're familiar with the old days, they used to do things like bloodletting, right? They thought we had to let the evil spirits out of the body. Or my favorite one is trepanning, where they would drill a hole in your head to let the evil spirits out. Probably better off with Excedrin or Advil or something like that. But having the wrong tool to debug the problem can often make the problem even worse. So one of the big problems we run into a lot when we try to debug concurrent programs is the behavior of the program in the debugger actually affects or doesn't reflect the actual behavior of the program when it's running in the wild. And this has actually got a name. It's called a Heisenbug, based on Heisenberg's uncertainty principle. And so the very act of observing the program can alter its state. I should probably show a Schrodinger's cat meme. I saw a picture of Schrodinger's cat. It said, wanted, dead or alive. So if you're a physics geek, that's ridiculously funny. Otherwise, it's like, what a stupid thing to say. So the very act of observing a program can alter its state. There's often lack of tools off the shelf that can identify and rectify race conditions, which we talked about before when things crash into each other and corrupt the state. And the lack of tool support means that you're often at your own, you have to rely on your own skills as a programmer debugger to track things down. That's one reason, by the way, we have all these unit tests for our programs. And you will come to both love and hate the unit tests. You will love them because they will find all kinds of problems with your code without having to go to TA office hours every time something goes wrong, or my office hours every time something goes wrong. You will learn to hate them because you'll be like, why is my code not working? It's not working, it's orange, it's red, I want it to be green. But the good news is it'll help you get your code to work if you follow the rules. But those things, those unit tests that we write are really, really, really complicated, as you'll discover if you try to read them. Conventional Java debuggers don't detect race conditions. You have to get very expensive tools that are typically add-ons, static analysis tools, dynamic analysis tools. And of course, as I mentioned before, the problems don't often surface until runtime. So even if you analyze your program statically with a static analyzer, still won't tell you all the problems there because they're only going to be invoked or surfaced at runtime. So how are we going to address this? Well, one way we're going to address this, sadly not very much in this course, although we will talk about it a little bit, is using Java's parallelism frameworks, things like the fork join pool or parallel streams and so on. And they reduce the complexity of synchronization by using a technique, which you're very familiar with, I hope, called divide and conquer. What's a good example of divide and conquer? Well, if you've taken the algorithms class here at Vanderbilt, you've most likely, and probably even the data structures class for that matter, you've probably been exposed to divide and conquer algorithms such as quicksort and merge sort and so on, where you take the whole thing and you split it up into smaller chunks and you solve those chunks one at a time or concurrently if you have a concurrent implementation and so on. And so we'll see that that's the way that Java's parallelism frameworks behave. They get rid of synchronization altogether by not sharing anything. So it's a very clever way of solving the problem. These frameworks largely eliminate the need for synchronization when writing concurrent and parallel apps. Now, there's some complexities that come with that as well, and it doesn't solve every possible problem in the space of concurrent and parallel computing, but it is very interesting. And if you take my sibling course in the fall, you'll learn all about this stuff. And we'll cover a little bit of it here when we talk about the fork join framework. So that's a quick overview of kind of the pervasiveness and complexity of Java synchronizers. We are now going to start looking in more detail at what Java synchronizers are.